representation of groups. Suppose we have a discrete group G with elements Gi. We already know that the set of non-singular square matrices of a given order form a group under matrix multiplication. Suppose we are able to assign to each element Gi of the group G a square matrix of order n, a non-singular square matrix of order n. This Gi is assigned a square matrix, non-singular square matrix Tji of order n, which satisfy the following condition, that for any two elements Gi and Gj of the group, Tgi times Tgj is equal to Tgij, then we can see that the assignment of square matrices, non-singular square matrices Tgi to every element Gi is in fact a homomorphism. So what we have is the following. We have a group G, and then we have a homomorphism from group G to the group of non-singular square matrices of order n. That means for every element Gi of the group, there is a non-singular square matrix Tgi of order n. And it satisfies this condition. So this condition Tgi times Tgj equals T of Gij for all Gi and Gj of the group G. Now, such a mapping is called an n-dimensional representation of the group G. It is n-dimensional because it is a mapping to non-singular square matrices of order n. The individual matrices Tgi are called the representation matrices, and the order of the matrices is called the dimension of the representation. In this case, the order of the matrices is n, and therefore this representation is called an n-dimensional representation. Now there are certain properties that the representation satisfy. If T is an n-dimensional representation of a group G, then the representation matrix Te of the identity element E of the group is the n by n unit matrix. So that is the first property. And the second property is that if we have an element Gi of the group, then the representation of Gi inverse, the representation matrix of Gi inverse denoted by Tgi inverse is equal to the inverse of the representation matrix of Gi. So T of Gi inverse is equal to Tgi inverse. True for every element Gi of the group. Now we can prove the first property, that T of the identity element is the unit matrix of order n, in the following way. First, we note that since E is the identity element, E times Gi is equal to Gi for all elements Gi of the group. Then we consider the representation T, then Te times Tgi, because this is a representation and therefore it is a homomorphism, this product should be equal to T of E times Gi. So that is what I have written here. Now E times Gi is Gi, and therefore this should be equal to T of Gi. So this implies that this left hand side, which is Te times Tgi, is equal to T of Gi for all elements Gi of the group G. And therefore this should be satisfied by all representation matrices TGI. And this is possible only if TE is the identity of the group of TGIs. And we know that that is the identity matrix. So if we have a set of matrices, and if some matrix TE times TGI is the same for all those matrices, is equal to TGI for all those matrices, then that means the matrix that we have, the matrix TE is the unit matrix. So that proves the first property of the representation. Now for the second property, we note that Gi times Gi inverse is the identity for all elements Gi of the group G. Now we take the product of the representation matrices TGI and TGI inverse. Now T is a representation, therefore it is a homomorphism, and therefore TGI times TGI inverse is equal to T of GI inverse. But then Gi inverse is the identity element of the group, so this is equal to T of E. But we have already shown here that the representation matrix for the identity element is in fact the identity matrix of order n. So this right hand side is equal to the identity matrix. So what does that say? The left hand side is TGI times TGI inverse, but that should be equal to 1. So that means that this matrix is in fact the inverse matrix of the first matrix. So we have TGI inverse equal to the inverse of this first matrix, TGI. So that proves both these properties. Faithful and unfaithful representations. A representation T of a group G is said to be a faithful representation if the distinct elements of the group are represented by distinct matrices. So that means if T is faithful and if TGI is equal to TGJ, that would imply that GI and GJ are the same. And if that is not true, that is, if a representation is not faithful, then it is termed an unfaithful representation. Unitary representations. If in a representation, all the representation matrices are unitary, such a representation is called a unitary representation. That means if a representation T is a unitary representation, the representation matrices TGI are unitary. So that means TGI dagger, that is the adjoint of the matrix TGI times TGI, should be equal to the identity matrix. But this can be true only if TGI dagger is the inverse of the matrix TGI. Or in other words, TGI inverse is equal to TG dagger. Now, as we have already seen, the inverse of the representation matrix TGI is equal to the representation matrix of the inverse of the element GI. So therefore, we have TGI inverse is equal to TGI dagger. Next, equivalent representations. Suppose we have two representations named T and T dash. So that means for every group element Gi, the T representation assigns a matrix Tgi and the T dash representation assigns a matrix T dash Gi. Now these two representations are said to be equivalent representations if there exists a non-singular matrix of the same order as this representation, same dimension as this representation. Suppose if T and T dash are representations of dimension n, and they will be called equivalent if there exists an n by n non-singular square matrix S such that for each Gi, T dash Gi is equal to S inverse Tgi times S. So for all group elements Gi, the same matrix S should satisfy this condition. And if this is satisfied, then we call the representations T and T dash equivalent representations. If two representations are not equivalent, obviously they are called inequivalent representations. Now, given a representation T of a group G and a non-singular matrix S of the same dimension, then we can always construct a new representation T dash by the following form: T dash Gi is equal to S inverse T Gi S. And we can show that this T dash Gi, the set of all such matrices, also form a representation of the group. So representation should satisfy two things. First of all, the matrices should be non-singular square matrices, and the second is that this mapping should be a homomorphism. So let us check whether these properties are satisfied by this assignment of square matrices to elements Gi of the group. First of all, we have already assumed that T is a representation and therefore the matrices Tgi are non-singular. And we have also assumed that S is a non-singular matrix. If S is non-singular, S inverse is also non-singular. So we now have T dash Gi equal to S inverse Tgis. All three matrices are non-singular, and a product of non-singular matrices is also non-singular, and therefore we see that T dash Gi are all non-singular matrices. Next, we check that they form a homomorphism. For that, we consider two elements Gi and Gj of the group and take the product of the representation matrices T dash Gi and T dash Gj. Now T dash Gi is S inverse Tgis. So we simply replace T dash Gi by that form. And T dash Gj is again S inverse Tgjs. Now these are all matrices, and the matrix multiplication is associative, and therefore we can take this product first, S inverse. But S inverse is simply the identity matrix, the unit matrix. And then the unit matrix times Tgi is simply Tgi. So what we have is now this S inverse, this Tgi, so S inverse and Tgi, and then this is identity times Tgj, which is Tgj, times this S. But now T is a representation and therefore it is a homomorphism, and therefore Tgi times Tgj equals T of Gijj. So we have on the right hand side S inverse T of Gijj times S. But from our definition of T dash, this is nothing but T dash of Gij. So we have the result that T dash Gi times T dash Gj equal to T dash Gij. So that shows that the mapping T dash is a homomorphism. So the matrices T dash R, T dash Gi are non-singular, and the mapping T dash is a homomorphism, and therefore it forms a representation of the group. So these two representations T and T dash are equivalent representations. Now the identity representation. Every group has a one-dimensional representation called the identity representation, in which every element Gi of the group is mapped to the number 1. So Tgi is equal to 1 for all Gi in the group. Now obviously this is a number, so it can be considered as a 1 by 1 matrix. So its dimension of this representation is 1, and we just need to check that it is, obviously it is 1, and therefore it is non-zero, non-singular. And we just need to check that this mapping is a homomorphism. For that we consider two elements of the group G. Let us take Gi and Gj. Then take the product Tgi times Tgj. But Tgi is equal to 1. Tgj is also equal to 1 in this mapping. And the product of those 1 and 1 is 1. Now we see that Gij is an element of the group G, and therefore the mapping T assigns again the number 1 to it. So we see that Tgi Tgj equal to 1, which is also equal to Tgij. So Tgi Tgj equal to T of Gij, and therefore this mapping is a homomorphism. So first of all, the matrix assigned, which is a simple number, is non-singular, and the mapping is homomorphism. And therefore this is a representation, and this particular representation is called the identity representation. And as we can see very easily that every group has one such representation. Basis for a representation. Let phi be a homomorphism from the group G to a group of invertible linear operators on a vector space V. By a linear operator on a vector space V, we mean a linear mapping from V to V. So that means given any vector V, any vector say A in V, the transformation T takes it to some other vector Ta in the same vector space V, with the property that T of A plus B, or maybe C1A plus C2B, is equal to C1 T of A plus C2 T of B, where C1 and C2 are scalars in the vector space V. An invertible linear operator or invertible linear transformation means the inverse mapping T inverse also exists. So we need to consider a homomorphism from the group G to a set of linear operators, invertible linear operators. If Gi is an element of say the group G, then phi maps it to phi of Gi, where phi of Gi is a linear operator in V. So that means under phi we can associate a linear operator, an invertible linear operator with every group element Gi. And this group element, this invertible linear operator phi of Gi is represented by a simple G hat Gi hat. And once that is done, we can define what is called a linear action of the group on the vector space V in the following way. So the action, linear action of the group element Gi on an arbitrary vector psi in the group in the vector space V is defined to be equal to the action of the invertible linear operator Gi hat on psi. So this is now well defined, and this action is called the linear action of the group G on the vector space V. Now this linear action has two properties. The first one is that given any vector psi1 and psi2 of the vector space and a1 and a2 of the field of the vector space, then the linear action Gi on the linear combination of vectors a1 psi1 plus a2 psi2 is equal to a1 times the action Gi on psi1 plus a2 times the action Gi on psi2. This can be seen as follows. Consider the action of the group element Gi on the linear combination a1 psi1 plus a2 psi2. The group action is simply the action by the linear operator Gi hat. So Gi hat acting on a1 psi1 plus a2 psi2. And since this is a linear operator, this is equal to a1 times Gi hat times psi1 plus a2 times Gi hat times psi2. But this is nothing but the group action on psi1. So a1 Gi psi1 plus this is the group action Gi on psi2. So this is equal to a2 Gi psi2. So this has proven that Gi acting on a1 psi1 plus a2 psi2 is simply a1 the action of Gi on psi1 plus a2 times the action of Gi on psi2. Now the second property is that for any two elements Gi and Gj of the group and any vector psi in the vector space V, the action of the element obtained by the product of group elements Gi and Gj, that is Gi Gj acting on psi, is simply equal to the action of Gi on the vector obtained by the action of Gj on psi. So that is Gi Gj, which is a group element acting on psi, is equal to Gi acting on Gj psi. To see this, we first consider the action of Gi Gj on psi, but that is nothing but Gi Gj is mapped to the non-singular linear operator phi Gi Gj, and we may also write this as Gi Gj hat, but I will stick with or stick to this particular notation. So this is phi Gi Gj, which is a linear operator acting on psi. But now this operation is also a linear, this transformation is also a homomorphism, and therefore phi of Gi Gj is equal to phi Gi times phi Gj. but phi gi is equal to gi hat and phi gj is equal to gj hat. So this is equal to gi hat times gj hat acting on psi. Now, from the composition rule for linear operators, this is equal to gi hat acting on the vector obtained by the action of gj hat on psi. But gj hat on psi is simply the action of gj on psi, and gi hat is simply the action of gi on this resulting vector. So we have gi gj psi equal to gi acting on gj psi. Now consider a subspace L of the vector space V. If we take an arbitrary vector psi in that vector space and consider the action of a group element gi on it, so the result would be gi psi, the action of gi on the vector psi. And if this results in a vector within L itself for all group elements gi and for all vectors psi in the subspace L, then we say that the subspace L is invariant or closed under the group action. So we consider a subspace of the vector space V, we call it L, and you take any vector psi in L and any element gi of the group, and if gi psi is a vector within L, then L will be called a closed under the group action. Or simply we may say that the subspace L is closed under G. Now consider, so obviously this is a subspace and therefore it will be spanned by a set of linearly independent basis vectors. And suppose we have say n linearly independent vectors that span the subspace L. So then the dimension of this invariant subspace will be n, and an n-dimensional invariant subspace can be represented with the subscript n also. So we will call it L subscript n. So Ln is an n-dimensional invariant subspace of the vector space V under the group action of G. So there will be n linearly independent basis vectors that span this space, and let us call them psi 1, psi 2, etc. up to psi n. Since they form a basis set, then every vector in the subspace Ln can be represented as a linear combination of these vectors. And secondly, since Ln is an invariant subspace under group action, and the vectors psi mu are elements of the vector space Ln, the action of any group element gi on psi result in a vector in Ln itself. So gi psi mu is also an element of Ln for every mu and for every gi. So that means gi psi mu is a vector in the linear vector space Ln. It is a subspace of V, so it's an n-dimensional subspace of n-dimensional space. And gi psi mu is an element of Ln because Ln is closed under the group action. Since it is a vector in Ln, it can be represented as a linear combination of psi mu's themselves. So that linear combination can be represented as psi nu multiplied by the corresponding coefficients and then sum over nu. So the coefficient corresponding to psi nu can be written as T nu. But now this is obtained from the action of Gi on psi mu, and therefore this coefficient should depend upon Gi as well as on mu. So we will write the second index mu here corresponding to the action of Gi on psi mu. We also have to represent or write the dependence of T on the group element Gi, and we will write it as T nu mu of Gi. So that means for every Gi and for every mu, there will be a set of n numbers T1 mu Gi, T2 mu Gi, and so on up to Tn mu Gi that form a linear combination with the basis vector psi nu, giving the vector obtained by the group action Gi on psi mu. So the linear combination will involve summation of nu from 1 to n. So that is this equation. And this should be true for every group element Gi and every basis vector mu. So there will be n such basis vectors, and there will be as many group elements as the order of the group G. So obviously these numbers T mu nu of Gi for a given Gi, so this represents a set of numbers with two indices mu and nu. Obviously nu runs from 1 to n and mu runs from 1 to n. So this set of numbers can be considered as the elements of an n by n matrix with the mu nth element given by the new muth element given by E nu mu. And there will be one such matrix for every group element Gi. Now considered as matrices, now these numbers, or this set of numbers, form a representation of the group G with the representation matrices given by these matrices. We now need to show that this statement is true. First of all, we need to show that these matrices are non-singular, and secondly, we need to show that these matrices form a homomorphism from the group to the set of n by n matrices. So to see this, we first note that T mu nu correspond to the action of non-singular T mu nu Gi correspond to the action of a non-singular operator Gi hat on psi mu, and therefore that operator is invertible, and therefore we will also expect this matrices T mu nu to have inverses as well, and therefore because of the way in which it is constructed, the matrices T are all non-singular, and they are square matrices obviously because their order is n by n. Next, we need to show that this mapping is a homomorphism, or in other words, we need to show that Tgi times Tgj is equal to Tgi Tj. For that, let us consider the action of Gij. This is an element of the group G because Gi and Gj are elements of the group G, and their product because of closure is also an element of G. So consider the action of this particular element represented as the product of Gi and Gj on a basis vector psi mu of the n-dimensional invariant subspace Ln of the vector space. But because of the property of group action, we have this equal to Gi acting on Gj psi mu. But from this definition, gi psi mu is simply a linear combination of psi mu's, which can be written as sum over nu running from 1 to n psi nu, then the coefficients given by these matrix elements t nu mu. Now the group element involved is gj, and therefore it is a function of gj. So gi act on this linear combination. Psi nu are the vectors and these are numbers. So it's a linear combination of these vectors, n vectors. And we already know that the action is linear and it satisfies this equation. So this summation can be taken outside, and then these are numbers that also comes to the left of this operator, this action. So this will be equal to sum over nu running from 1 to n t nu mu of gi times the action of gi on the vectors psi nu. So gi acting on psi. But again, using this, we have gi psi nu as a linear combination of psi mu's. So gi psi mu should be represented as a linear combination of psi mu's. So consider the roth basis vector psi rho. It will be multiplied by corresponding coefficient, call it t rho, but then this is obtained by the action of the group element on psi nu, and therefore the nu index should come here, and it depends upon gi because it is the action of gi on psi nu. So this is equal to gi. Now I need to write down the linear combination, that is sum over rho running from 1 to n, and that is exactly what we have done here. We have replaced gi psi nu by this summation. Now these are finite sums, and therefore I can take this summation first and new summation second. So I will take this to the left. So when I do that, I have sum over rho running from 1 to n, then this psi rho that is over here. Then the remaining factors depends upon nu. So I have to write the new summation here, and then the first number is t nu mu gj, and that is this, and then t rho nu gi, and that is this. And if I consider tgi and tgj as matrices, this is simply the rho mu element of the product of the matrices tgi and tgj. So that means we have this equal to sum over rho running from 1 to n, then psi rho, but now this is equal to simply the rho mu element of the matrix product tgi and tgj. Now look at the action of, say, gi on psi mu. This was written as sum over nu running from 1 to n psi nu t nu mu gi. And if instead of gi I consider the group element obtained by the product of gi and gj, and that acting on psi mu can also be written as a linear combination like this, but in that case this will become summation nu running from say, instead of nu, let me write rho running from 1 to n, then psi rho t rho, this is mu, and therefore we have t rho mu of, instead of gi I have gi gj here, so gi j. So from this I have gi gj acting on psi mu given by sum over rho running from 1 to n psi rho, then t rho mu gi gj. But this is exactly same as this, and the right hand side of this is given by this, and here it is given by this. A comparison of these equations will have, the summation having the same form, have psi rho here and psi rho here, and there is a matrix whose rho muth element appearing here. Here also I have a matrix whose rho muth element is appearing here. So that means this matrix is exactly same as this matrix, or in other words, T Gi Tj is equal to T Gi times T Gj. And in fact, this is what we were looking for. That means these matrices T Gi for every Gi form a representation, because it satisfies T Gi Gj equal to T Gi times T Gj. So this mapping is actually a homomorphism. And as we have already seen, these matrices will be invertible, non-singular, because they are representations of invertible linear operators on the vector space. So what we have done so far is the following. We considered a vector space, considered the linear action of the group elements on the vector space. And then we considered a subspace of the vector space having the property that if we consider the action of the group elements on any vector in that subspace, the result will be in the subspace itself. And such subspaces are called invariant subspaces, or they are said to be closed under the group action. Then we consider an n-dimensional invariant subspace of the vector space under the group action. So obviously that space will be spanned by n basis vectors, and we call them psi1, psi2, etc. up to psi n. Then the action of any group element on one of the basis vectors will also be an element of this n-dimensional subspace itself, and therefore should be able to be represented as a linear combination of these basis vectors themselves. And that leads to a representation of the action in terms of matrices corresponding to the group element, and that defines a set of matrices. And these matrices form a representation of the group. Then these basis vectors here that we have used to find out these representation matrices are called the basis vectors or the partners of, or the basis functions of the representation. So a set of vectors psi1, psi2, etc. up to psi n in a vector space is said to be a basis for the representation T of a group, provided group given by the matrices Tgi for every element Gi of the group, provided under the group action they transform according to this rule. Okay, so we have a set of vectors psi1, etc. up to psi n, and if under the group action they transform according to this rule, then they are said to be the basis vectors for the representation of the group given by these matrices Tgi, one matrix for each group element. The individual vectors psi1, psi2, etc. are called the partners or the basis vectors or the basis functions. Now, basis for equivalent representations. Let the set of n vectors psi1, psi2, etc. up to psi n form a basis for an n-dimensional representation T of a group G in a vector space V. And we consider an equivalent representation T dash. So given a representation T, we can construct an equivalent representation T dash, provided we also have a non-singular square matrix of the same order as the order of these representation matrices T. So for each group element Gi, we can construct matrices T dash denoted as T dash of Gi as equal to S inverse Tgi times S. And we have already seen that the matrices T dash form a representation of the group. So T dash and T are equivalent representations. And the basis vectors for the representation of T of the group are psi1, psi2, etc. up to psi n. So these matrices T are n by n square matrices. We now define n new vectors, which we denote as psi dash mu, by means of a linear combination involving these matrices S, these matrix elements of S. So psi dash mu will be written as sum over nu running from 1 to n psi nu S nu mu. And we have already said that S is a non-singular matrix, and therefore an inverse exists for this matrix S, and that can be used to invert this equation. In the matrix form, this can be written as the row vector psi dash, which is defined as, say, psi dash. Row vector can be written as, say, psi1 dash, psi2 dash, etc. up to psi n dash. So once we write it that way, and similarly the row vector psi as psi1, psi2, etc. up to psi n, then this equation is the same as psi dash equal to the row vector psi multiplied by the square matrix S. Now since S is non-singular, S inverse exists, and therefore we can multiply this equation from the right with S inverse. So we will get psi dash times S inverse equal to psi S times S inverse, but S times S inverse is the identity matrix, and therefore this is equal to psi. So if I want to find the muth element of this row vector psi, so psi is equal to now psi dash S inverse, and psi mu is obtained by this is obtained from the matrix product psi dash S inverse, and the corresponding element would be sum over nu running from 1 to n psi dash nu S inverse nu mu. And that is exactly what we have got here. Now consider the action of a group element Gi on psi dash mu and the vectors defined by this equation. So that will be equal to Gi acting on the linear combination sum over nu psi nu S nu mu. But the group action is linear, and therefore this goes inside and acts on psi nu, and this coefficient go to the left. So we will have sum over nu running from 1 to n S nu mu, then the action of Gi on psi nu. But we already know how Gi act on nu, because psi nu are the basis vectors for a representation T of the group G, and therefore Gi psi nu or psi nu is transformed in the following way. This will be given by the linear combination, say row running from 1 to n psi row T row nu Gi, and so this is replaced by equation. Now we have psi row sitting here, On the left hand side, I have written the action of gi on psi dash mu, and I would like to have the right hand side also represented in terms of psi dashes. But we have already seen that I can write psi mu's in terms of psi dashes. So similarly, I can write psi rho also in terms of psi dashes. So look at this equation: psi mu equal to psi dash nu S inverse nu mu. That's a summation over nu running from 1 to n, and therefore psi rho will be equal to sum over, say, some index nu or eta running from 1 to n, then psi dash eta, then S inverse eta, that is, we substitute this equation for psi rho here. So that's what we have done here. Now we note that these are all finite sums, and I can take this summation to the left. That is, I can perform this summation as the last summation, and I can perform these summations before this one. So taking this to the left, I have sum over eta running from 1 to n. Then I have this vector psi dash eta here. Now these other factors, S nu mu, S inverse eta rho, and T rho nu, etc., depends upon nu and rho. So I write the summation over rho and nu here, and then I have this guy first. So S inverse eta rho, then this guy T rho nu, and then I write this guy. That is okay because these are all numbers. So I can rearrange them in whichever order I want. So I write this first, this second, and this third. So I have S inverse eta rho, T rho nu, then S nu mu. And the summation is over rho and nu. We immediately identify this as the eta muth element of the matrix product of S inverse TS. So we see that this is equal to S inverse TGIS, then the eta muth element. But what is S inverse TGIS? And this is nothing but the equivalent representation T dash of GI. So on the right hand side, I have sum over eta running from 1 to n, psi dash eta, T dash eta mu GI. So which tells us that the matrices T dash are in fact, as we have already seen, a representation of an equivalent representation of the group G, and the corresponding basis vectors for the representation matrices T dash are psi dashes. So the result is the following. Suppose we have a representation T of a group, and the basis vectors for this representation are, say, psi 1, psi 2, etc., up to psi n, and then we can construct new vectors psi 1 dash, etc., psi n dash, using the transformation psi dash mu is equal to sum over nu running from 1 to n psi nu S nu mu. Then this set of vectors form a basis for the equivalent representation of the group G, which is equivalent to this representation T. So with T dash given by S inverse T. So this also tells us that if we have two equivalent representations, that means their basis vectors are connected by a linear transformation. So, given a representation of the group, an equivalent representation corresponds to a choice of a new set of basis vectors formed by an invertible linear transformation of the basis for the original representation. Adjoint representation of a group. Suppose we have a group G and it has a representation T. So that means for every group element Gi, there will be a representation matrix denoted by T of Gi. Then, so now consider for a group element Gi, consider its inverse and consider the representation matrix for its inverse, T of Gi inverse, and then take its transpose. And we denote the transpose of a matrix by this symbol. We will put T as a superscript. Okay, and call this matrix as T tilde of Gi. So, given a group element Gi, and a representation T, we take the representation matrix of Gi inverse and then take its transpose and call it T tilde Gi. So that's what we have done here. We now claim that T tilde Gi, which is in fact a mapping from Gi to set of non-singular square matrices of the same order as this T, and they form a representation of the group. First of all, since T is non-singular, the transpose of T is also non-singular, and therefore the matrices T tilde are non-singular as well. So the first requirement for the representation matrices is satisfied. We just now need to show that if we have two say group elements Gi and Gj, then T tilde Gi times T tilde Gj is equal to T tilde of Gi Gj. To show that, we consider the product of T tilde Gi and T tilde Gj. But then T tilde Gi is simply the transpose of T of Gi inverse. It's written like that. And similarly, T tilde Gj is the transpose of T Gj inverse. So it's a product of transposes of the transposes of two matrices. But we know that the transpose of a product is given by this rule. So A B transpose is equal to B transpose A transpose. So if I consider T Gj inverse times T Gi inverse, both are matrices, and take the transpose of that, I will get T Gi inverse transpose and T Gj inverse transpose. And that is exactly what this is. Therefore, this is equal to this, the transpose of the product of these two matrices. Now, T is a group representation, and therefore it's a homomorphism, and therefore Tgi Gj inverse times Tgi inverse should be equal to T of Gj inverse times Gi inverse. But we also know that AB inverse is equal to B inverse A inverse, and therefore Gi Gj inverse is equal to Gj inverse times Gi inverse, and that is this. So this can be written as Gi Gj inverse. So what we have is the transpose of T of the inverse of an element given by Gi Gj, which is nothing but T tilde of Gi Gj because of this definition. So what we have now shown is that the product of T tilde Gi and T tilde Gj is in fact T tilde of Gi Gj. And therefore, the matrices T tilde form a representation of the group. So what are the basis vectors for this representation? So let phi 1, phi 2, etc. up to phi n are the basis vectors for this representation. So that means from our earlier rule for the transformation of the basis vectors, Gi acting on phi mu should be the linear combination given by summation over nu running from 1 to n, then phi nu, then the representation matrices, they are denoted as T tilde nu mu Gi. But this is nothing but the transpose of T tilde is nothing but the transpose of T Gi inverse, and I have to take the new muth element. New mu. But the new muth element of the transpose matrix is equal to the mu nuth element of the matrix. So this is equal to T mu nu of Gi inverse. So I replace this by T mu nu of Gi inverse. So the transformation rule under the adjoint representation is the following. So Gi phi mu is equal to sum over nu running from 1 to n phi nu, then T mu nu Gi inverse.